Welcome back, everybody. In this video, we will build upon what we've learned about gases to understand how to deal with not uniform or single identity gases, but gas mixtures. We've learned already that many assumptions about gases can get us basically all the way there to our understanding using the ideal gas equation of state, or treating gases as if they behave ideally, which is to say that all different types of a gas behave the same, right? One element of oxygen will behave the same as one molecule of the element nitrogen. They all behave according to the ideal gas law and with ideal behavior. But what we're going to see is that when we're dealing with mixtures, there are certain ways that we need to consider their contributions to the overall total gas properties. And we're going to first focus on water, as that's a common, we'll say, contaminant in many different gas mixtures that you may have. Most notably, that when we're running reactions, we'll often collect a product gas over water, which means that there will be some water vapor within that mixture, and we need to account for that water vapor in order to get accurate readings, calculations, and understandings of what we've collected. We will extend this idea of how gas mixtures work to just general mixtures of gases and get to know about the partial pressure of a gas, which is the pressure that only a single component of that mixture will exert. And we'll see how we do a few calculations of this and better understand how the different properties of mixtures can be used to understand the overall collection that we have. Alright, so lately we've been studying partial pressure and vapor pressure, and I would start us with an example problem. Definitely give this one a look and pause and see if you're able to come up with the correct multiple choice answer. So the question is that we have a vessel of gas collected over water that's been brought to atmospheric pressure. We have the volume, we have the temperature of the lab, and we want to know how many moles of the unknown gas are present. And key to this problem is that the vessel is collected over water, right? So even though we have a sealed collection flask, we know that that sealed collection flask contains not only the gas of interest that we're collecting, but it also contains water, right? And we can assume that the partial pressure of water in the collection flask is going to be equal to its vapor pressure, right? That is to say that it will be saturated, right? Okay, so why don't you pause the video if you like and see if you can come up with the correct answer here. Alright, so how do we break down this problem? How do we get started, right? So again, the key thing is that the vessel of gas is collected over water. And so we have a mixture, right? And in that mixture, we know that the vapor pressure of water will be equivalent to, its vapor pressure, right? The partial pressure, I should say, is equivalent to its vapor pressure. And here that value at 19 degrees Celsius is 16.5 torr, millimeters mercury, whatever you like. So here's sort of a diagram of our setup, right? And we know that within the collection flask, right, where we've collected the gas over water, the partial pressure of water is 16.5 millimeters mercury, 16.5 torr. And the total pressure is going to be 1 atmosphere, right? Atmospheric pressure, we'll go ahead and assume, is 760 millimeters mercury as well. And so if we know that this is a gas that contains the water vapor from the vapor pressure, as well as the pressure of the gas itself, then we know that the unknown pressure here is going to be 745.5 torr as well. So that is the rest of the partial pressure, right? The partial pressure of the unknown plus the partial pressure of the water, which we calculate from the vapor pressure, gives us 1 atmosphere. That is our atmospheric pressure. That is the total pressure within this flask. And so we can now just use PV equals nRT with the partial pressure of the unknown, and we'll obtain that it's 0.0112 moles. And, critical here is to note there is no partial volume, right? The water and the unknown both occupy the entire volume of this collection flask. What's different is their number of moles and their partial pressure, but they both exist at the same volume and at the same temperature, right? The temperature at 19 degrees Celsius and the volume, they each occupy the entire 275 mil volume. I'm going to go ahead and pause the video here, or rather you should pause, and then we will discuss. Alright, so the student is again collecting a sample of gas over water. We are at atmospheric pressure, so again, let's just assume that that's 760 millimeters mercury, 1 atmosphere. And we have a volume that we're collecting. The lab is a certain temperature, and here I've even given us the vapor pressure, but you should be familiar with how to obtain this, as well as where in OpenStax you can find the vapor pressure, right? Table 9.2. And so again, the question is how many moles of gas were collected? And so, let's keep in mind again that the partial pressure of our sample is going to be the total pressure minus the partial pressure of the water. And here, right, we can calculate all the following things in the same way. And we see that the partial pressure of the sample is going to be 760 millimeters mercury for the total pressure minus this 26.7 millimeters mercury that is the vapor pressure of water. And note that when we have a warmer temperature and the vapor pressure of water is higher, that at a given total pressure, we just aren't going to have as much of the gas sample, right? It's sort of filled up with water already, and if it's only going to reach a certain total pressure, then, there will be less sample that we're able to collect, which is not, a bad or a good thing really, but definitely something that you need to keep in mind. And note that still the sample is, the really large majority of the total pressure here, right? The volume is 265 mils, so 0.265 liters. We have our temperature. We know R, which we've been using in the following form, liters atmosphere per mole Kelvin. And we're going to calculate the N of the sample, so the number of moles of the sample, which we can do using the ideal gas law again, right? We can calculate moles and partial pressure just by using those values within the ideal gas law. And we obtain a value of 0.0103 moles. That's the number of moles of this sample gas. And so a second question could be, how many moles of water are present in the flask? And you should have worked through this one as well. And now I will preface by saying that the most straightforward way is just to calculate it as we did the previous problem, right? Just by using the vapor pressure of water as the pressure of the water, and then calculating the moles of the water that must exist that way. But, with these partial pressure equations, sometimes, maybe you don't see that most direct route at first. And so I'll pose an alternative solution that also arrives at the right answer. Try to focus on, again, the qualitative definitions of, partial pressure and mole fraction, right? The mole fraction is the amount of one component of the system in terms of a fraction, right? So the percent divided by 100, 0.5 meaning 50% in other words. And that the partial pressures add up to the total pressure, and that those partial pressures exist in proportion to their mole fraction. So if a mole fraction of a component is 50%, then the partial pressure of that component will be 50% of the total. So following those, right, there are really a lot of ways to get from point A to point B, and here's how I did it. So first note that the partial pressure of water is the vapor pressure of water, right? This should be something we're comfortable with by now. Note that we can get the mole fraction of water by taking the partial pressure of the water vapor, dividing it by the total pressure. And so because we know that the partial pressure of water is 3.5% or 0.0351, excuse me, is the fraction of the total pressure that the vapor pressure of water is, so pH2O over P total. That's the same as the mole fraction, because we know that the gases contribute to the total pressure as their partial pressure in accordance with their mole fraction, right? So the fact that the mole fraction is 3.5% means that the vapor pressure is 3.5% of the total pressure. And from this, we can determine, well, of course, that the number of moles of H2O is based on the total number of moles according to this percent, right? If we take the moles of H2O divided by the total moles, we'll also get 0.0351. And so we can calculate the total number of moles based on the total pressure, and we obtain that the total moles is 0.0107 moles, so slightly higher than the moles of the sample. That is to be expected. And finally, we can use that equation for the mole fraction, rearrange so that it's the mole fraction of the water multiplied by the total number of moles to give us the number of moles of just the water, and we obtain the following. And again, this should be the same as what you obtain if you just go ahead and use PV equals nRT from the beginning using the vapor pressure of water. But I think this does a good example of showing us how to manipulate and use the mole fraction and partial pressure equations. And again, I think that these may look a little daunting perhaps, but if you're able to recognize those principles, right, that I mentioned before, that the partial pressure is equivalent to the mole fraction multiplied by the total pressure, which qualitatively means that the partial pressure is the contribution from each gas, which is proportional directly to its mole fraction. All right, here is our second question. So we have a mixture again, and we want to determine the partial pressure and number of moles for each gas in the following vessel, which contains a mixture of xenon and neon, and we have the total pressure, and we have the mole fraction of one component. So the question is, how do we determine basically the mixture, right? We want to know the number of moles of each gas, we want to know the partial pressure of each gas, and all we're given here is the mole fraction of the first gas, and in addition we have the overall pressure, volume, and temperature of the system. Do pause and give it a try. So first of all, let's remember our mole fraction equations. And again, these are really reflective of gas behavior, and it's really essential to understand the concepts that they represent. And the first one here, Ni, meaning the number of moles of some component, is equal to Xi, meaning the fraction of that component within the mixture. So again, if it's 10%, then this Xi would be 0.1, multiplied by the total number of moles, right? So if it's 2 moles total and it's 10% Xi, then the number of moles of component I, which is Ni, would be 0.2 moles, right? So pretty straightforward there, I think, as well. And that the partial pressure behaves exactly the same, that the partial pressure of that component is equal to the mole fraction of that component times the total pressure. So again, if we have 5 atmospheres and it is 10%, then the partial pressure of that component would be 0.5 atmospheres, right? And that is to say that that is its contribution to the total pressure. If it's 10%, it contributes 10% to the total pressure. So I think pretty straightforward again. Don't get too bogged down in the definitions and the equations. Follow that, that sort of qualitative look. So first thing we need to do is we need to get the total number of moles, right? Because while we have the mole fraction, we will need to know the total number of moles to get there. But we have all the information we need. PV equals nRT. We have pressure, volume, and temperature data. We know R, and so we can go ahead and calculate using the ideal gas law and obtain that the total number of moles is 4.11 moles, right? That's the total number of moles here in this system. Okay, so what do we do next? Well, let's keep into account that we know the mole fraction of the xenon, right? It's 0.761, in other words, 76.1%. And key here, right, is that we may need to know the mole fraction of the other. So if we know it's a binary mixture, meaning it only has 2 parts, what is the mole fraction of the other component? And that is going to be 1 minus this, right? We know the mole fractions have to add up to 100%, or 1. And so if it's just these 2 pieces, right, if it's 76% one thing and the rest something else, it's going to be 23.9%, right? That adds up to 1 there. 0.761 subtracted from 1 is 0.239. And so if we have a binary mixture, right, and we have the mole fraction of one component, we have the mole fraction of the second component. From this, we can calculate the number of moles of either component. Let's start with the neon, right? 0.239 is the mole fraction. Multiply that fraction by the total number of moles, and that's basically like taking 23.9% of 4.11, and we obtain that this is the number of moles of neon. Do the same thing for xenon, and we can actually just do this by subtracting that number of neon moles from the 4.11 moles that are total, right? If it's the 2 of them together, then that will be true. So either way you want to do it, you'll obtain that the xenon is 3.13 moles. Finally, to get the partial pressure, we do really the exact same thing with the total pressure. The xenon is, again, or the neon here, excuse me, is 23.9%. Because it's 23.9%, it will be making up 23.9% of the partial pressure. Its partial pressure, rather, is 23.9% of the total pressure, and that is 1.6 atmospheres. And we do the same thing with the xenon, right? And obtain 4.90 atmospheres. Again, you can just go ahead and take the total pressure of 6.50 atmospheres and subtract the partial pressure of neon. Because it's a binary mixture, that will work as well, and we get the same answer. And so again, this is our partial pressure example, right? We've taken a flask that has known pressure, volume, and temperature information, therefore we have the moles, and we've calculated the moles of each component and the partial pressures of each component based on their mole fraction. Okay, so that is our examples here. Again, want to point out that both components occupy the entire volume, right? Their partial pressure means that they kind of are each contributing a low pressure, which add up to the total pressure of 6.5 atmospheres, but they both occupy the whole 15.75 liters. And that, again, I think is something worth mentioning. There is no partial volume. They don't occupy sections of the container. They both are making a solution and therefore occupy the entire container. Both gases do this.